Welcome today. I wanted to welcome you to the fourth in our series of 5 courses, online short courses. This is me, of course. You recognize that gorgeous face. I have been with Solid Applications since 2017 and doing SolidWorks application engineering work for about 15 years now. So during the shelter in place of the coronavirus pandemic, we have been offering these condensed lessons for users. So just reviewing what we've done thus far, on May 4th, we did a basic intro to the workflow and some detail on meshing and contacts. We did a restraints and fixtures lesson on June 2nd. We did one just a little over a week ago on June 18th, applied forces and loads. That was a good one. And this one today will be on materials and some practical tips of working with materials and the parts folder, of course. And then we'll have understanding your results, July 7th, which really means working with in post-process mode to make sense out of the plots, the different results you can get. So today's lesson, we'll be working on materials. And when you say materials, you're also talking about the parts folder and how parts are treated. So one could say that the title to this presentation really should be working with materials in the parts folder. All of these presentations are available online. The 3 previous ones have the Watch Now button. The ones that have not occurred yet have the Register button that you see over here. Just so you know, they will be available in case you want to catch up on some of those. And so let's talk about what our intent is today. I kind of want to give an overview of what can be done with parts and materials in the parts folder, basically. I'm going to give you a walkthrough of some of the, pretty much everything I can think of, and maybe I'll be covering some things you haven't seen. Maybe you'll learn a little bit about how things work, okay? The benefit, what I want you to do is to basically be able to define your parts appropriately to the intent of your study. There may not be one best answer. I want you to know what the options are. So the topics, very brief catch up, as I've been doing on all these, just, you know, the Venn method of working through the study tree. We're going to be looking at the parts folder, and then within the parts folder, solids, shells and their definition, including sheet metal, shells, and modeled surfaces. Beams and their definition, that will also include weldments as well as just naturally skinny items. How to exclude items from an analysis, treating an item as a remote mass, the use of split lines. Now, I find that the use of split lines is very important. I use it all the time, and that's one of the tricks that I want to show you. It's nothing new, but people might not think about using it all the time. Material selection, how to basically pick a material for your model, and the use of custom materials, categories of materials, libraries, and then what data do you need to have in a material. That will, you'll actually see that in the material selection section, but we're gonna make a custom material, and then we'll go from there. Okay, so one thing I'm going to tell you is that this lesson is about pre-processing, not showing sexy plots or animations. So don't expect any of those. All right. So the first section, I'm going to cover a large chunk of these items on our agenda, and we'll go from there. All right. And oh, what the heck? Here's a sexy animation. Right. There you go. All right, good. No, we're not supposed to show sexy animations or plots. Okay, so I'm going to move on from here. All right. So that's as good as this engineer's sense of humor goes. So all levity has been dispensed with. So now we can get down to business. Right. Okay. So our review catch-up slide. Here is a short picture of the study tree. As you know, I work off of right-clicking any of the folders to get where I need to go. In other words, the right-click yields fruitful menus. Typically, if you right-click the parts folder, you're only going to have a couple of options in this case that really really are useful. One is going to be applying materials to all bodies. One is going to be applying a favorite material. So more often, what we'll do is we'll simply expand it, and that's going to be found over here where the little drop-down arrow is. and that will turn the entire parts folder open. It will expose all the parts in that list to you. So that's really what I work with most of the time in the parts folder. So what might be in the parts folder? Well, here's a picture of a model we're going to be working with today. And in this model, I put in pretty much every type of modeled body you can have so that they show up in a full comprehensive variety in the study tree. So one of the things you'll see is assigned materials. So you look over here, you can see stainless steel, A36 steel, various materials applied to each of the bodies. You'll see solid bodies, and the icon for a solid body looks like this guy here, kind of a little curved blocky thing. You will see surface bodies. Now they come in two flavors. So the first flavor is for something that you've modeled as a surface. If you do an extruded surface or some kind of complicated shape out of a surface, those are infinitely thin surface bodies in SOLIDWORKS. They'll be meshed as a shell in your sim study. Also, you're going to have to define those bodies. So if you haven't done anything to them and you try to run your study, you'll get a message saying you need to define it, which is no big sin. You just go and do it then. Anything that's converted from sheet metal in SOLIDWORKS will come in as a surface, as a shell mesh item. And that will be predefined, but you can edit it within reason. It's still going to be defined as a mid-surface, whereas if you define something with a surface body, you can apply the thickness to one side or the other, or a mid-surface, or with any combination of thicknesses on either side. So sheet metal is somewhat editable. You can change the thickness from what it was in SOLIDWORKS. Beams. There you see beams. How do you recognize a beam? It's got a little beam icon on it. Who would have thought, right? So anything that is a weldment in SOLIDWORKS will default to being a beam in a simulation study. It doesn't mean you can't change it, but that's what it comes in as. And then if you have modeled long, skinny items with a constant cross section, then you might want to treat them as beams, in which case they will acquire the beam icon. So in the parts folder, what can I do? You can assign material to a part, to multiple parts, like you see here. I've got two parts selected, or all parts. Now, I say parts, and in simulation, they call them parts. They call it the parts folder, but a more accurate name for this would be the bodies folder. Because one of the things to remember is that SOLIDWORKS Simulation does not care if they're parts or if they're bodies in a multi-body solid part, or if they are surfaces. It just doesn't care. It sees them all essentially as bodies. As long as they're defined, it's happy. So you'll notice that the model I made up for demonstration purposes here is a multi-body part file with all different kinds of bodies in it. And the study tree doesn't really make much of a difference, doesn't really distinguish. It just looks at it and says, these are all the bodies I've got, and this is what kind of body they are. So when I say parts, I'm not referring literally to parts, and you'll see that in the demo data set that I have, which is all one part, but many bodies. So you can assign material to a part, to multiple parts, or to all parts. You can also exclude, or you can reverse that by doing it again, to include bodies from a study. So you simply right-click a body and you choose the option exclude from analysis. If it's already excluded, it will show up gray, and then you can right-click on it and include it in the analysis again. So there's a default option in simulation, which I see no need to turn off, which is to hide any body that's been excluded when you are in the study. You go back to your model in SOLIDWORKS, it shows up again, but when you're in the study, once you've excluded something, it's hidden. When it's excluded, it might as well not be there. You could actually call this within the study suppressing the model, suppressing that body, okay? But it's not suppressing it in SOLIDWORKS, it's essentially suppressing it in the study. So it's not there, it might as well be hidden. You'll see it in the tree, but it's not in your model. Now, what that means is suppressing parts in SOLIDWORKS is not necessary in a study. Now, that doesn't mean it won't be practical to sometimes suppress parts or components in a study, in SOLIDWORKS before you get to the study. If you have lots and lots and lots of parts, it might be easier to work in SOLIDWORKS and make a separate FEA configuration and suppress many components. The downside, though, of suppressing things, especially in assemblies, is you lose all the mates that go with those suppressed components. So if you have many, many things to suppress, you know, it may be a good idea to do that in SOLIDWORKS ahead of time. It's just less picking and clicking. But once you're in the study, you just need to know that you can simply exclude any number of parts from that study, and you don't have to actually suppress them in SOLIDWORKS. Now, one of the other things to bear in mind is you might actually want to make some parts be different. And once you get into that area, you're really talking about making an FEA configuration of your study with FEA configurations of parts. But that's a different story. So right now we're just talking about the fact that you can exclude bodies, and one of the nice things about that is that it means you do not have to suppress parts in SOLIDWORKS as often as you might have been doing in the past. Treating beams as solids, that's another thing we can do in the parts folder. So you can see here there's a beam, and we right click it, we can choose the option to treat it as a solid. So it will no longer mesh as a beam with a joint on each end. It will actually be a solid and get a mesh just like any other solid. You can also treat any sheet metal component as solid. So you see here, this is the icon for a sheet metal component as opposed to a flat surface type of component. This is a sheet metal component, and you can right click on it and treat it as a solid. Because it started out life as a solid, it actually is a solid, isn't it? All right, what else can we do in the parts folder? You can right click any body and you can treat it as a remote mass. So what does that mean? Well, first of all, why would you do that? It's for complex parts that you have no interest in analyzing. Think about it in terms of, you know, that complex engine block part. You're not analyzing the engine block. You want to account for its mass and the effect it has on the rest of your bodies. So you need to select what faces to attach it to. I'm going to use this as an example to show you the split face. And then you have to know that it must be modeled accurately. So if you're going to model it out of, you know, if you don't give it a material, then it's going to have the mass that it would have as if it were made out of water. So you need to actually figure that if it's an engine block and it's made out of a certain kind of aluminum, that you give it the correct material and it's been modeled pretty accurately, then its center of mass and its actual weight will be applied correctly to your study. One of the things that this is typically used with is when you apply gravity or you apply a centrifugal force to your model. So that's mostly what it's used for. If you don't apply gravity or centrifugal force, you might as well just exclude it or treat it as a remote load instead of a remote mass. All right, so that said, let's keep moving on from what I can do in the parts folder. And let's start getting a little more specific and look at solids. So in SOLIDWORKS, anything that's modeled as a solid body, which is, you know, I would say most things, they're going to default to SOLIDWORKS to solid bodies in simulation unless they are sheet metal or weldments. That's just basically the way most people think. So in many cases, you can just leave that alone. But one of the other things to know about solids is that if you right-click one of the solids in the tree, and I mean right-clicking one of these guys here, you can redefine any sheet metal shells as solids, as I mentioned a moment ago. So there's a sheet metal body, you right-click it, and you treat it as solid. You can also redefine beams as solid. So here we're getting down into a little bigger picture of what we saw before, treat as solid. And one of the other things you can do with a solid is that you can take a solid and turn it into a shell. Now, let's be very specific about what that means. It says define shell by selected faces. So let's say you modeled a box. You know that you're going to refer to just its outside surfaces. Let's say all but one side, which is open. Let's say it's an upside down box that's open on the bottom. You would then pick the four sides and the top side and use those as the faces to define a shell, and it will then apply a thickness that you define on those faces. So this is a way of saying, look, I don't need to model everything as surfaces. I know I'm going to model this as a solid with the intention of turning it into a shell when I make my study. And one of the beauties of that is you could then, let's say, run several studies in which you change the thicknesses of the shell as defined. So this is a way of turning faces on a solid into shell mesh items. You'd be choosing the faces, you would be hitting the green check, and what happens when you completed this, the solid body is going to go away. There will be a surface body icon here, and the solid body will go away. So you won't have that solid body in the study anymore. With any shell, you can edit the definition by simply right-clicking on it and choosing Edit Definition. That includes the sheet metal shells, but I'll show you what that looks like. So what does a shell definition dialog look like? First of all, you can define whether you're going to use the thin or thick formulation. I would say for 99% of what you're going to do, you're going to be using the thin formulation. We can show you a picture, I guess, or if anybody has any questions about this, email me. I'll send you some screenshots of the page in the manual that describes the difference between thin and thick formulation. But for most people who are using shells, something is much thinner, has a much thinner thickness dimension than it does its characteristic length and width dimensions. So it's a different formulation to treat the strain, the way it deforms through the cross section. So I find I use thin almost all the time. If it's going to be a thick formulation, most of the time I might as well mesh it as a solid. We also have control here in the shell definition dialog of our thickness, of course. We can decide what side our thickness is going to go on. So you can make it a mid surface, top surface, bottom surface, or split the difference with various thicknesses. So this is where you get to choose how you want it oriented. And this is one of the things that always has in the past kind of thrown people about using shells. Like, I can't really tell what side I'm looking at. And you have an option for a preview, and you're going to want to use the full preview on this because it will show you the actual surface that is being used to define the shell, and then it'll show you what side of that surface the thickness is being applied to. Now that thickness can be applied to one side or the other. You can also flip which side is considered the top and bottom side. So when you mesh, if you have not done any shell mesh studies yet, you'll notice that one side of your shell mesh is orange, that's the bottom face, and one side is going to be kind of a grayish face, and that's the top face. Now when you're looking at the preview, the top face shows in green, the bottom face shows in orange. So you're flipping these colors without actually flipping the orientation or the side to which the thickness has been added. All right, so where this matters is in a mesh. You don't want to have faces that are all next to each other, joined at their edges, where one of them is showing orange, and next to it you're seeing something showing the top face. So you don't want bottom and top face edge to edge. You want to at least get everything aligned with each other, where you can flip those shell elements. So that's one of the things that you can control over this. So you can go, for example, if you have it wrong, you can always just go flip the shell top and bottom here. This is one of two places you can do this. So the top and the bottom is what the program considers to be the top and the bottom face of the shell. Now let's talk about beam definition. So, most people, when they think of beams, are thinking of, steel structures or aluminum structures. Weldment bodies in SOLIDWORKS will default to beams automatically. You can right-click that beam and you can treat it as a solid, in which case it acquires the solid body icon. If you right-click it again, you can go back and choose Treat as Beam. Now, short beams, where the characteristic length is over width, that ratio, the length over width ratio is less than 10, those really don't fit the beam assumptions. Now, you should see when you hover over a beam like this, you'll see a little message. But what tips you off to what's going on is the fact that there's going to be a little I symbol, and that's this guy right here. So what that I symbol means is that you should pay attention to it. So oftentimes people just kind of ignore these things because, you know, no problem has been found. They just kind of just breeze right through this. This may or may not be important, but generally the beam assumption is not met when you have a model that looks like this. All right, you'll notice that this particular one has coped ends, so it's very short, and plus the end effects are not really normal to a beam. So that said, pay attention to the I symbol. You'll see a little message pop up, but the problem in 2020 right now, there seems to be a little bit of a bug in that you hover over one of these short beams with the information symbol, and this message shows up for about a quarter of a second. You can't really read it very well, and you can't right click and say what's wrong and find it. So in previous versions, this would actually hover, this message would stay when you're hovering. So when you see this I, it's generally a symbol that means your beam is awfully short and the assumptions probably don't apply anymore. That's a good reason why you'd want to right click on it and treat it as a solid. So when you're looking at your beams, one of the things to notice is below the parts folder, there is a joint group. It's another folder. So if you don't have any beams in your model, in your study, I should say, then you won't have a joint group. The moment you have one beam, there's a joint group, and the joints are these little balls. So if you have the free end of a beam, if it's not attached to another beam, it will be this gold color. We have a more unflattering term for that color. And then where the beams meet, where they join each other, you can see here there's a long beam that meets this kind of a transverse beam. You will have this fuchsia or pinkish or mauve color. Okay, you can see I really know my colors, right? So that indicates there might be a free end. So in this particular picture, you can see that this may have come in as a beam if it was a weldment, or it may have been defined as a beam in the study. This guy here is not a beam. He's been treated as a solid because this beam shows the joint as a free end. Think of the leg of a table, at the bottom of a table leg, that would have a gold end on it. Okay, so the gold ones are free ends and the fuchsia ones are joints. Now, if one beam butts into another beam somewhere in the middle, if its end butts into another beam in the middle, it will be a fuchsia color. It won't be considered a free end. So when I say free end, I mean free, it's on its own, it's not, doesn't have anything to do with any other beams. Okay, now the joints can be recalculated. Here you see a picture of the joint group. You simply right click on the joint group and you choose edit. And the dialog looks like this. Whenever I edit my joint group, I leave the selection on all, and I hit this calculate button. It's automatic. It may sometimes change the order of numbering for your for the joints, but those will get reattached. I would say in the bad old days, maybe 10 years ago, you might lose attachments. You might have to redo some of your contact conditions. So one of the things to know about these joints is that they can, you can make contact conditions, you can apply loads to them, you can apply restraints to them. So when you apply, you can make a joint contacted to the side of a beam, that sort of thing, or to a face of a shell. So you edit, you say calculate, it recalculates. Now I will also tell you that the need to recalculate is rare. Because simulation has gotten really good at updating any geometric changes or any choices that you've made in the study that change the joint group. For example, taking a beam and treating it as solid. Now you've got fewer joints, and the character of the joints changes. So just in setting up the model for this study, I've reaffirmed for myself that the joint group automatically updated when I treated a beam as solid, and then I went back to that solid and said treat as beam. The joint group updated automatically. It generally, I don't seem to have any issues with this. The need to recalculate the joint group is almost at this point for me kind of superstitious based upon what I know of history. I really only do it if a study is being particularly troublesome to me. And mostly that's kind of like kicking the tires and figuring that I'm going to fix the engine, right? Beam definition. You can edit the actual definition of any beam by simply right-clicking on the beam and choose Edit Definition. And what do you see when you edit the definition of a beam? Well, you're going to have a bird's eye view of the joints. Now you can turn it into a truss, in which case the end points are have no resistance to rotation at all. Or you can individually address the beams. So when you're individually addressing them, you notice that they're color coded here, so you can see which beam you are dealing with. When they color coded the beams, do you think that was an enhancement request? Yeah, I think it was a pretty good enhancement request, and when that came out, I thought it was a really great improvement because it made it much easier to know which beam I was talking about. So you can make that end rigid, which is going to be the default typically. You can make it a hinge in which it will bend in one of two directions. You can make it a slide joint, in which case it's free to slide along. The end of one beam is free to slide along the other beam. Or you can manually define it, get way down in the weeds. And this is a lot more control than most people want, unless they're doing beams in machinery, moving machinery, or unless they have a special need. So the point being here, you have a lot more control available than you're likely going to need. All right, so let me jump on the example now, and I'll go into SOLIDWORKS here. So first of all, let me go into the SOLIDWORKS side of things in the model. So in this model, I've modeled a few things as plain old solids. So we've got this guy here. He's a simple solid, right? Just a plain old extrusion with a couple of counterbore holes put in there with the hole wizard. I've done a couple of weldment items. You see there's a weldment feature. There is an L angle feature with 3 L angles in it. And then there is a square tube, and I trimmed that square tube to the L angle bodies. So that's where this trimming comes in there, right? So you can see what that guy looks like on his own. If I isolate, all right. So most production people don't want to see this kind of curvy coping. They want to see stuff with chamfered angles on it, which is also supported in that trim tool. But I did that just because I wanted to make a complex end shape on here for the purposes of demonstration. Then I did a sheet metal body here. You can see the sheet metal, the base flange. So that's sheet metal of a thickness of, how thick is that? That is 3 millimeters thick. And so that's a sheet metal body. We know that's going to come into the study as a shell. And then I modeled a surface loft. I wanted to model something, with a little bit of shape complexity. Sheet metal, you could do that in sheet metal, but it models a little more easily in as just a thin, infinitely thin shell model. So that's what we've got in our 3D CAD model. So I'm going to go to the study here, and one of the first things you'll see before you notice anything else is the joints. So let's work top to bottom here, okay? So there is a green check here, which means all the materials have been defined. Now, some of these materials have come in from simulation. So let's go back here, and if I expand some of these guys, you'll see that this piece of sheet metal is 316 stainless steel sheet, whereas this guy is 304 stainless. All right, and then we have some of these other bodies that are taking the default metal of for this whole part of A36, which is typically used in structural steel. All right, so we have a few different materials here, and they're coming through already. Now this guy here, this is our sheet metal shell. So I'm going to right click on him, and we're going to edit its definition. Now note again, you can treat it as solid, you can treat it as beam, you can treat it as a remote mass. You can also make it rigid. I don't do this very often, but if there's something you just want to treat it as if it's not going to bend, if it's something that's monolithic and really strong and it's not going to flex very much, and you don't want to have to analyze its flexing, you can make it rigid. That occasionally used to have little glitches associated with it. I think it's pretty much better today. Probably my prejudice and habit is that I don't use it very often, but I encourage you to experiment with it. So I'm going to edit the definition of this shell just to show it to you. So what I can control here is I can control the actual thickness. All right, so if I go in here, I can flip the top and bottom of the shell, and I could also go in there and treat it as a solid and then treat it as a shell from that. So I could right click on this guy, right click, I could say treat as solid, and then knowing that it's a solid, I could right click and say define shell by selected faces. And I could select all of these faces here on the outside, for example, and say I'm going to treat this as a 2mm shell. So I've gone the whole route of treating this as a solid and then only to set it up as a shell. So here you can see what I've done. The material is being applied to the outside, so I'll flip it to the other side. 2mm thick. Let me make it 5mm thick so it's thicker than the other one. There you go. And what's the bottom face and top face? Well, the top face is the green side, so I'll just flip those. The material is still on the same side. The thickness is applied on that side, but now the bottom face is over here. All right, so that's the kind of thing you can do with sheet metal. All right. Moving on down, here is my surface body, this lofty thing, right? So let's click on it, and if I look at it, I'm going to have to edit its definition. So right now it doesn't know how thick it is. So I can say this guy is going to be 2.5mm thick. And again, I will apply the thickness to one face or the other. I'll probably want to apply the thickness so that it is added to the outside, so that, because people don't like to see this thickness applied in such a way that it interferes, although your study will not fail if it does that. It's very forgiving about applying the thickness in this direction. Any contact bonding you make, let's say between this edge and the edge of your sheet metal, is going to work no matter what side you put the thickness on. But people don't feel comfortable with it, and rightfully so, to apply the thickness going into the body. So I understand that, and I'm the same way. And then of course you can flip what side is considered the top and what side is considered the bottom. All right, so as you look at it, you'll see the colors changing. All right, so once you defined it, then you are able to move on with your study. It's fully defined. You just need to make sure it has the material. All right, so here we have a solid body. And pretend with me, if you will, that this is really complicated. And I'm really not interested in the body except insofar as the effect it has on the rest of the study bearing its weight. Right now, it's made out of 304 stainless, a fairly heavy material. So what I want to do is I want to treat it as a remote load. But I'm going to do something first in SOLIDWORKS Simulation, which is I'm going to open up a sketch on this face. What I'm going to do is, if I make this into a remote load, I have to apply it to a face, obviously this face, but I don't want it attached to the entire face. I want to attach it to a face right where it's likely to be attached. So I'm going to open up a sketch right on this face. I'm going to zoom in on this and do a select other and pick the bottom face of this component and convert the entities. So I'm going to use that to build a split line on that face. And I will project it. I'll project this sketch onto that face. And now I will have split out that surface. So if I were to hide this component, you'll see that that's a separate surface from this one. Okay, so far so good. So let me bring that component back. Now in my study, I'll find that component in the tree by simply clicking on it out here. Right click, treat as remote mass. And what face am I going to apply it to? Now look at this. I can apply it to joints. I can apply it to a beam itself, or I can apply it to faces, edges, and vertices. So I'm again going to select that face down in there. And I'm going to select the face down at the bottom there, that face there, and apply it there. Oh, that is the same face as the component. So let me flip this over select it from the bottom, right click, select other, right click, and then select that face. That should work. There we go. So you get the idea. To treat it as remote mass, you need to select the face where it's going to go, and then I'm going to apply that force from its CG. So you can then define with a coordinate system or whatever you want at a CG of your choice, or it's going to automatically be at the CG of the component. So that's what you do with treating something as a remote mass. And then, of course, down in your external loads, you'd be creating either gravity or a centrifugal force. Okay. Moving on down here, there's our solid body. There's one beam. There is our beam in the middle, and that's the one with the little eye symbol. And you'll see here, now today this message is staying, so you can actually read the whole message. The slenderness ratio of the beam, L over a characteristic dimension, length over a characteristic dimension, which is the depth of the width, is less than 10. So this is telling me, you know, that's not such a good beam. It doesn't really follow the beam assumptions of something very long and skinny. So I'm simply going to right click on it and treat it as a solid. Now I want you to pay attention here to the color of those two joints, because they are fuchsia, because that's where this longitudinal beam and this transverse beam meet. Same thing here. So when I click on this guy and I right click on him and I say treat as solid, now suddenly those joints actually moved, and they are no longer intersection joints. They are free end joints, because I've got a solid body, but as far as the beam is concerned, this beam is hanging out in space. Now I might want to add a contact condition between this joint and this body, and between this joint and the same body here, but that's, you know, further to your study setup. Okay, now something else we have here, here's our latest beam now, shows the icon as a solid because it's no longer a beam. If I want to right click it, I can go back and treat it as a beam. Okay. Next item in here, we got this guy. Now, you know, this is a classic example of something that would work as a beam, but it wasn't modeled as a weldment, so it didn't come in by default as a beam. But I want it to be a beam because it makes sense, right? I don't want to mesh two elements thick through this. So what's my radius here? My radius is like 8 millimeters, and my outer diameter is 8 millimeters. My outer diameter is 12 millimeters. So I've got 2 millimeters of thickness. So we're talking about a 1 millimeter mesh all the way through this guy. I don't think so, not really. It's not my favorite thing to do, put a super fine mesh 2 elements thick through that guy. So I'm going to right click on him and say treat as beam. And you'll notice once I've done that, that this guy acquires the beam icon, and there's no little information I telling me that it's that the assumption doesn't really fit. Okay, so now I have this beam over here, and then I have this back beam on the end. Now let's make up a story and say, for whatever reason, I don't want this guy in the study anymore. I'm gonna, you know, he's not really performing any task or something like that. So I'm gonna right click on him, and I'm just gonna say exclude from analysis. And you'll notice that the joints change color. These are now free ends, right? If I right click on him again, and by the way, see he's grayed out as if he were suppressed. I right click him on again, and I say include in analysis. The joint moved over, and now it's an intersection joint. All right, so I've done a lot of changing of things that come in as beams. So I'm going to right click on the joint group, and I'm just going to say edit, just so you can see what's in there. So these are all the joints we've got. All right, and we've got 6 different joints, and I'm just going to say calculate all, and it just calculates them all. It recalculates. Now it's no big deal. It used to be kind of a little dicey, but it works pretty well. All right, so having done that, one of the other things you'll notice is that you can see that the neutral axis can be displayed on a beam joint, so you can actually see where it is relative to the piece of angle here. all right? And it'll also display the shear center. And these are kind of color coded. It might be hard for you to see on your end. So the joints have been edited. And I believe I've run through pretty much everything on here as far as the definition of the bodies themselves. So now let's just see. We've actually covered pretty much everything in here, even remote mass, up to now. So the next thing we're going to cover is selecting your materials. So generally, when you're selecting a material, this probably for most of you is very elemental. You've probably done this before. Anything in SOLIDWORKS carries over into a sim study. You can redefine it, you can change it. So if you've made your entire part out of plain carbon steel, or your entire model out of plain carbon steel, you can then go edit it and change it. Again, you can also apply material to the parts folder. So that will be another way to apply one material to everything and then edit a few that are different. When you copy a sim study, this is just a little thing to think about in your strategy. Well, let's say you're going to run a study several different ways. I would say try to get as much set up in that first study as you can. And then when you copy the study, everything comes with it, including part definitions and materials. So if you've turned a piece of sheet metal into a solid, or if you've turned a solid into a beam or whatever, when you copy your study, it'll come across like that. So you might make some changes down the road. You might add some contact sets, take some contact sets away. That will require a new mesh, but at least all the part definitions are going to be the same. All right, now you might be comparing part definitions. So you might be running 3 studies with one thing as sheet metal shell and another 3 studies, the same studies as, as a solid, but you at least should get everything set up in each study that you're going to copy. It'll save you time. So when you have a green check on a body, that means it's defined. That means it's defined in terms of what kind of body it is. If it's a shell, it means it knows what its thickness is and what side the thickness is applied on, and that it has a material. Now, most of us think of the green check meaning it's got a material, all right? When all the bodies in your parts folder have been defined and all materials have been applied to all the bodies, you have a green check on the entire folder. Okay, good to know. So you run your study, it says material isn't defined or thickness is not defined for one or more bodies. That just means, oh, let me go back and look at my parts folder, find out who's missing what. You might have defined a material, but maybe you didn't define a thickness on a shell. Oops, just go define it. It's no big sin. Okay, right-clicking on a body or bodies. So all you do is do that and apply a favorite material. The favorites material is going to be in a list of things that you've designated as favorites. Not a big deal. To be fair, I don't use it very often. If you like it, and if you work with 6 different materials all the time, it's a real time saver for you. I work with every material under the sun, so to me, I really don't have any favorites that mean anything to me. You can apply or edit a material, and that'll bring you right to the material database. That's typically how I work, and I'm going to be usually using either one of the standard SOLIDWORKS or the SOLIDWORKS DIN materials. So the database is pretty self-explanatory. It's just a hierarchy. It has categories within each of those databases. Like here's the zinc alloys category, and within the categories, it will have materials like this zinc AC43A. Okay, now, what is in a material definition? What matters to SOLIDWORKS simulation? Well, look at the items that are red, look at the items that are blue. The ones that are red are generally considered required. Now, I gotta be cautious in saying that they're required. The ones that are required by the calculation tool in simulation is the elastic modulus, which is the stiffness of the material. That's the stress over strain curve, Young's modulus, which is a straight line slope. So that number represents a slope of a line. And then the Poisson's ratio. So for example, a lot of times the modulus of elasticity for a lot of similar materials is very similar, if not identical. And the Poisson's ratio is usually similar. Steels usually range between 0.29 and about 0.31. Most of them are just under 0.3. Elastic modulus for most standard steels will be somewhere about 190,000 to maybe 220,000 for simple carbon steels. On the other hand, a high strength alloy steel will be like 620,000. Excuse me, that's the yield strength. Sorry, getting a little bit ahead of myself here. So when you have a similar elastic modulus, the behavior in the study will be the same if these two values are about the same. So you might think you're applying a much stronger material, but you're not applying a material that's much stiffer. So the actual flexing of the stresses you'll see will usually be about the same unless there's a massive difference here and you go from steel to aluminum. So what changes is the yield strength. And yield strength is an interesting property of a material in SOLIDWORKS simulation because for years it was not required. And then I think about 5, 6, 8 years ago, they made it required. The yield strength is not used in the calculation except to put that little arrow in your color plot if you've gone beyond yield. And it will point to where the yield stress is. If the yield is in the orange region, anything that's red and above orange is at plastic deformation. But that's not used in the calculation. It's just kind of a pointer to tell you where on the scale your yield strength is. And if your entire study result is below yield strength, they'll just tell you in a little, it'll show up at the bottom, just telling you what the yield strength is. So if your highest stress is 160 megapascals, then it'll tell you that your yield stress is 206 and you're happy. Then they made it a requirement for a while. And it seems like in 2020, they removed yield strength as a requirement again. But you can see that in mine, it's still shown as a red property, which would imply that I would have to have it if I'm going to define a custom material. But I think they just didn't change the color display in the table. So it seems that in 2020, my experience thus far has been that they've removed yield strength as a required property if you're going to use it for a study. Wow, okay, good. Now, density, that's another one. Density is not needed for a linear stress strain study. It doesn't enter into the calculation. It matters if you're going to apply gravity or if you're going to apply a centrifugal load. Suddenly, now density is important. It matters if you're going to go into simulation professional and do a buckling study or a frequency analysis. Yeah, or a drop test. Now density, plays a very important part, right? But for a plain old regular, I'm going to bend this bar study, no, density is not crucial until you're applying gravity. All right, so you don't have to have density unless those types of forces are in your study. So the parameters are listed in this table. The required parameters for a linear static study are elastic modulus, Poisson's ratio. Nice to have, yield strength, a thermal expansion coefficient. Yeah, if you're going to be applying a thermal load to your study, thermal expansion coefficient is what's used to make your part expand or contract and cause stresses, okay? For other study types, thermal conductivity and density, okay? Thermal conductivity if you're going to be doing a thermal study in Sim Professional. Basically, if you're running a study now and you want to make a custom material, you need the elastic modulus, you need the Poisson's ratio. I would be trying to get a yield strength, and it's hard for me to say what kind of a decent material definition it is if I don't have a density. So I just think density is one of those things that I would always want to have. You can't really know what your model weighs just in SOLIDWORKS alone unless you have a density to the material, right? Okay, so density is a good thing. Yeah, it should be in the nice to have column. All right, so we'll jump to the example and we're going to go take a look at just defining some materials. All right, so let's take a look here. I'm going to go to this guy here, this body, and right now he's made out of A36. So all I'm going to do on this body is right click and go to apply edit material. You can see what my favorites list looks like. Apply edit material. I get the entire database. It's where I last looked. Let me collapse it. Those are our DIN materials. You'll notice a lot of various types of detailed steels that are used in European design shops. It's actually a good database. There's your basic SOLIDWORKS materials. This is not a super comprehensive database. If you look at the steels, there are not even 2 screens full. You know, it's a pretty decent selection, but one of the things I want to call your attention to is look at some of the properties of, let's say, 1023 carbon steel sheet. The elastic modulus is 205,000. I want to make sure my units are in megapascals, all right? This is one of the biggest gotchas, and I'm going to mention this in a few minutes, looking at the wrong units. So about 205,000 for the elastic modulus. The yield strength is 282, okay? Poisson's ratio is 0.29. Let's go down here to 1020 stainless. 200,000 elastic modulus, 0.29 Poisson's ratio, but the yield strength is 350, right? Whereas here, the yield strength was 282. So it's considerably stronger, the 1020. But the behavior, the flexing I'm going to get, the stresses, the deformations, if you run the 2 identical studies with these 2 materials in it, your behavior is going to be the same. Your plot's going to be just about the same. This is very slightly less flexible. Let's go down to plain carbon steel. All right, plain carbon steel, 210,000, 0.28. Yield strength 220. It's less strong than either of them. So what that means is that they all behave about the same, but the yield strength is different. So if I exceed yield in my study, if let's say if I would exceed yield in all 3 of them, you know that your stress result in that range isn't real accurate above yield, but you know that if you simply made a custom material and increased the yield strength to accommodate that, it would be a good result. Okay, so you simply pick a material. I'm going to pick 1023. We're going to say, okay, apply and close. Done. Now it's taking on a new material. Another thing you can do when you're applying materials is you can simply pick the whole tree, apply material to all bodies. You either do this because you want the same material in all bodies, or let's say you have 25 bodies and 3 of them are going to be different. Apply the same material to all bodies and then alter the 3 that are different. That part is really easy. So this part I'm sure you all know about. I'm not going to bore you all any further with how to apply a material because it's pretty basic. So I just covered the basic simple material selection. But now let's talk about custom materials. Okay, so with custom materials, I'm going to talk about categories and libraries and again, what information is needed. So what we normally do is I typically will start with a material that's similar. I mean, if I'm really going out in left field with a material I've got no experience with, I'll look up the data somewhere and then I will make a brand new material from scratch. But typically I'll take an existing material, I'm going to right click it and copy it, and then I'm going to paste it into a category in the custom materials database. The very next thing I'm going to do here, I'm going to put this 304 into the steels category in the custom materials database, and then I might make a new category if I'm copying an aluminum or something like that and I don't have an aluminum category, I might make a new category. New library, be a little bit cautious about that because every time you do that, you're creating a new SLDMDB. It's a material database, and you don't really want to just throw a whole bunch of databases on there. I would just as soon make a new category and throw it into the category on my existing custom materials database. So the next thing I would do is I would rename the material, and then I would edit the mechanical parameters, all these numbers in here, and I would make sure that I'm setting everything up with the right units. So that's actually what I would do first, but that's, like I said, that's a major gotcha. You discovered that something is behaving like it's made out of the stem of a plant, and then you realize you gave it a number thinking you were putting in megapascals, but you were putting in pascals. And you have to take that heel of your palm to your forehead and go and edit your material. And then you hit the actually the save button and the apply button. Okay. So that's how you would create a custom material and apply it to your part. So I'm going to go do that in the example here. So let's just pick any old part. Let's pick this guy again. I'm going to go there. I made him out of carbon steel sheet. I'm going to go apply, edit material. That's the material we're starting with. I'm going to actually go to something like, I'll go pick that same 304 stainless. I'm going to right click, copy him, scroll to the top and collapse this whole database. I'll go to my custom materials. I'll go to my steel. I will apply. I'll paste it in there. And right now it's just a pure copy of this. All right. So I'm going to make this 440, which is a fairly, it's quite a bit stiffer, but it doesn't have a super high yield strength. So this elastic modulus is more like about 225. And it tends not to neck down a lot. It's a little more brittle. So the Poisson's ratio, which is the neck down ratio, that is going to be a little higher. Yield strength is also, it's a little higher, but man, when this material goes, it's used for stainless tooling fairly often. So the yield strength is about 280, 282 megapascals, and thermal conductivity, which if you're going to use it in certain types of components actually matters. It's a little lower, so it's about, 12.5. All right, there you go. So that's all you're going to get of me adding numbers together. And I'm going to save this guy. I've given it a new name. Save it, and I'm going to apply it. And there we're done. So now you can see that the material is on this guy is the AISI 440. You can also, when you're editing a material, you can also change the appearance if you want it to look different. So you can go in here, you can pick different types of appearances, and it will behave differently. Save it, apply, and then it'll take on a little bit of a different appearance, especially if you're using RealView. I usually don't use RealView in my work, so I tend not to show that. Okay, so that is, in a nutshell, custom materials. One other thing I might want to cover in here is if you've got Simulation Pro or Premium, you have access to the Materiality SolidWorks Material web portal. And if you click on here, it says you have to have a subscription for it. Okay. And it brings you to this web page. I was a little reluctant to show it to you because my experience is when I chase down materials here, my success on these 4 databases is spotty. Sometimes I'll be looking for a particular kind of plastic and I'll just come up with a complete treasure trove of all different types of particular kind of plastic. And other times it's a complete goose egg on all 4 databases and everything like that. So you'd be wanting to look, for the most part, I guess, if you're just running with linear static studies, linear static isotropic material, you'd be looking in the classes of a particular kind of metal or plastic or rubber. For example, you can see right here that the material types is fairly limited. Even the types of metals is fairly limited. But, you know, when you get there, you can start looking through various types of materials. Click a database, hit locate materials. Every time you back out because you don't like the material selected, it brings you back to the same page and you need to select everything all over again. Another thing is that if you have SolidWorks Simulation, you have a kind of an intro access to MatWeb, which I find to be a little better place to chase down materials. So that's my preferred way of looking, but this is available. Feel free to play around with it. And you know, you'll see if you go there, you'll actually get some data information, and you can download this as a material. It will come in as a separate material database, which will show on your list, which is why you might have a separate database. It came from the materiality database right here. So each one of these is a separate database, just like this whole custom materials database is. Doesn't mean you couldn't then take a material or a category and copy it in here and get rid of the extraneous database, but it will come in as its own database. All right, so I just wanted to throw that out to you, and you access that here if you've got the Sim Pro subscription. All right, so we've now covered custom materials, categories and libraries, and the data that we need. Again, it's going to be yield strength, Poisson's ratio, elastic modulus, Poisson's ratio, and secondarily yield strength and density are the important ones. All right, so I will say at this point that this is me done, having gone through all of it once or twice, and really appreciate your business. I want to let you know we've got one more of these coming up, and the reception actually has been pretty good. People really have liked these presentations, so we might be presenting another series after this. So this one was today, working with materials and a couple little tips on them, and then we're going to have a pretty extensive presentation on going over the post-processing, not only looking at the charts, but your results options. So all the things you can do to a plot to really gain insight into what's going on with your study, the chin rubbing stuff. So that's going to be the next one. These presentations are all available online. Again, if you want to catch up on any of the previous ones that you might have missed on the Solid Apps website, you can find them. And this last one will pretty soon become a Watch Now icon. Thank you for attending, and we really do appreciate your business, especially during this lockdown period. And my advice is always follow the material evidence, as Sherlock Holmes said. All right, that's it.